Hello, hello. Once you can see and hear me, please say hi in the chat. Hi, everyone. If you were here last week, let me know. If you are brand new today, let me know as well. And everyone in the chat, make sure that our newbies feel welcome. Hi, Raway. Hello. Who else do we have? Ishak. Hello. Welcome back. Amrita. Lovely. Lillian. Hi. Henry. Hello. And thank you for your comment on my TikTok, Henry. Really appreciate it. Hi, Andreas. Welcome back. Make sure as well, just while everyone's coming in, if you are not yet subscribed to this YouTube channel, make sure that you press subscribe now. And at any point during the lesson that you feel like, yeah, I really like this, make sure that you press like on it as well. Also, make sure that you're following, if you have TikTok, I understand if some of you don't, but if you do have TikTok, make sure that you're following my TikTok channel as well, because I post just exam question tips and just kind of some problem solving as well for A-level chemistry. So the channel is LaJoy Does Chemistry. So make sure that you're following over there and have a look. There's quite a few videos up already, and we're just kind of posting lots and lots, getting you ready for the new year and throughout the year as well. Okay? Hello and hello again. Okay, Eben Oluwa, Nessa, hi. Hi, Miran. Hi, Jay. Lovely. Okay. It is 11 on the dot. So we're going to get started. For today's lesson, such an important, I mean, they're all important. Hi, Grace. All of the lessons, of course, are important. Morning, Zakir. But the lessons that I've chosen for the summer school are specifically because they are going to make you feel, hopefully, the most prepared for the first topics that you cover in year 13. So we're looking at Hess's law today, so energetics, because one of the first topics that most students tend to do in year 13 is thermodynamics for AQA, which is all your lattice enthalpy stuff. And so we need this stuff to be really secure so that that can then be applied to the more tricky year 13 stuff. Okay, morning, Sienna. So we're going to start with some definitions, definition recap. What is enthalpy? Does anyone want to type the definition in the chat? Okay, our definitions for energetics and thermodynamics need to be on point. We're often asked definitions questions in this topic. Absolutely. Okay, so those are the first two words, Sienna and Grace. Absolutely. So heat, energy, and then Rihanna's got the next word. So heat, energy, change. But at the moment, that's not enthalpy. This is the change in energy, but enthalpy. Okay, actually, to be fair, enthalpy change is heat energy change. Let's just keep it as heat energy, seeing as I haven't said enthalpy change. I've just said heat, just said enthalpy. Heat energy, not necessarily standard conditions, because enthalpy changes can be done at a number of different conditions. We just define standard enthalpy as standard conditions. I'm going to add the last few words. Heat energy at constant pressure. That's your enthalpy definition. Okay, and if they ask for heat enthalpy change, then it would just be heat energy change at constant pressure. Okay, now again, it doesn't necessarily have to be standard conditions. So standard conditions where we've got 100 kilopascals, that's standard enthalpy, but just general enthalpy, the pressure just needs to be constant. Okay, the way that is very, very common for students to realize actually what is enthalpy. Okay. We're going to keep going because we've got a lot to get through. Hopefully, you've got the workbook rather, in front of you, and also have a calculator because there's a lot of maths today. I've got two, I don't know, just in case. I think it's important to have a spare calculator, just like you have a spare pair of glasses. Okay. So, standard enthalpy change of reaction, that is the heat energy change at constant pressure, or just the enthalpy change for a particular reaction under standard conditions. And in the chat, can you remind me what are the standard conditions when it comes to enthalpy changes? So we need a standard temperature and a standard pressure. Absolutely. So we use a temperature of 298 Kelvin and a pressure of 100 kilopascals. Okay, specifically at AQA, we put 298 Kelvin, 100 kilopascals. Okay, and you're absolutely right, Jay, as well. If we were dealing with any solutions, then we would want those to have a concentration of 1 mole per decimeter cubed. Okay, now standard enthalpy changes of any reaction we can often measure directly. And oh, have I skipped a slide? What's your next slide? It should say this direct measurement of enthalpy changes, right? And then we'll come back to the other two. So direct measurement of enthalpy changes, and again, we're not going to spend much time on this at all because this could be a whole lesson for itself, right? But when we're looking at standard measurement of enthalpy changes, that's when we're looking at Q equals mc delta T. Okay, and then we turn Q, which is just the heat energy transferred. Oops. And we turn that into enthalpy change, which is delta H, by doing negative Q over the number of moles, and then also divided by 1,000 to turn your value into kilojoules per mole. Okay, that's when we do our calorimetry experiments. And the reason that oh, Zakir, good question. I'm going to answer that in a second. The reason I've split the page in half is because there are two main calorimetry experiments that we'll see at A level. So we've got our combustion calorimetry, where we have our spirit burner with our fuel. We have our copper calorimeter with water in it, and then pretend that's all being held up by, a clamp and a clamp stand. It's not floating in midair. And then we measure the temperature difference, and then from that can measure um, enthalpy change. Okay, so coming back to Zakir's question, the reason I put minus Q is because if we link our two expressions together, then for an exothermic reaction, let me just change my color. For an exothermic reaction, the temperature increases, right? So your delta T will be positive, which will make your Q positive, and so minus Q will make your delta H negative, which we know it should be for an exothermic reaction, right? Whereas for an endothermic reaction, our delta T, because temperature decreases, will be negative, which will make Q negative. And so then minus Q will come out as positive, and we know that endothermic changes, the enthalpy changes are positive. Now, for this, I'll give you a choice, right? You don't have to put the minus in here if you don't want to. As long as you remember at the end, before giving your final answer, that if it's exothermic, you put the negative sign there, and if it's endothermic, it's positive. Okay, so you can leave the negative out of the expression and just put it in at the end. But I like to put it in there just because it's a really, really common mistake. A lot of students lose the last mark for enthalpy calculations because they forget to make their exothermic enthalpy change negative. So by putting it into the expression, you don't forget. Okay, does that answer your question? Okay. Oh, and J, divided by moles, absolutely. But then we also divide by 1,000. And that's because Q is measured in joules, right? Whereas our enthalpy change is in kilojoules per mole, which is why we have that divide by 1,000. Again, you don't need to put the divided by 1,000 in the expression itself, as long as you remember to divide by 1,000 to go from joules to kilojoules. But again, I like to put it all into the expression so that we don't forget. Okay, Imana, today we're not covering thermodynamics or entropy because that's typically a year 13 topic. And for this course, we're essentially going over the core year 12 stuff to get you ready for year 13. But in the full course in year 13, thermodynamics, entropy, that's the first topic that we'll cover. And I'll talk to you about the full course at the end of the lesson. If I forget, please remind me, okay? But have to and want to talk to you about the main course so that you can all get into that with a massive discount as well. Okay. Again, quickly going through our other calorimetry experiment setup. So this is our combustion calorimetry. And then we've also got the solution one where we have our polystyrene cup. And then our reaction is just happening in here. And again, we're measuring the change in temperature. This is linked to your RP2, where that links to, the graph and all of that stuff. Again, we're not going to go into that in detail today. That is a whole lesson for itself. Today, our focus is on Hess's law. And Hess's law, that's when we can't measure the enthalpy changes directly. So we have to do them indirectly instead. And often for Hess's law and measuring enthalpy changes indirectly, there are two key types of enthalpy changes that we use. And so I'm going to go back 2 slides, but that should be the next slide in your workbook. And that's standard enthalpy change of formation and standard enthalpy change of combustion. So let's start with formation. And again, definition, so important. Can I have the definition for standard enthalpy change of formation in the chat? And they always start the same. All of your enthalpy change definitions will start with the enthalpy change when, and then dot, dot, dot. Orla, wonderful, fantastic. Couldn't have said it better myself. Wonderful. Jay, I would just add that last bit at the end. So talking about the standard states. Fantastic, Zakir. Okay. So 1 mole. I should really just copy and paste it from the chat because you've done it so well. Enthalpy change when 1 mole of now you said compound. Typically we do say compound, but I agree with Grace. We can just say substance, but compound works as well, is formed from its constituent elements, or we can just say from its elements under standard conditions. And then that key bit at the end, all reactants and products in their standard states. And state symbols are so important when it comes to energetics. And that's because all of these definitions are linked to the state that your reactants and products are in. So whether you're writing definitions or whether you're writing equations, make sure that state symbols are always included, or a description of what state you're dealing with. So let's do a couple of examples really quickly so we know how to write equations for enthalpy of formation, starting with sodium chloride. Let's pretend there's a bit more space there. So again, we're forming 1 mole of a substance from its elements. So we're forming sodium chloride, NaCl, from its elements, and the elements must be Na and Cl2. Okay, this needs to be balanced, and we cannot add any numbers into the front of the NaCl because, as you've all correctly said in your definitions, we're only forming 1 mole of the substance. So we might need to use halves or any other fraction to make sure that this product, the substance that you're forming, is only ever just 1 mole. So looking at this would be half a mole of Cl2 with 1 mole of Na to produce 1 mole of NaCl. And of course, if you wrote this as your equation, which is typically just worth 1 mark, you're not getting that mark. And why are you not getting that mark? Because you haven't got the state symbols. So we need their standard states. Sodium is a metal, so it would be solid. Chlorine, we know from our group 7 topic, is a gas at standard in its standard state. And sodium chloride as an ionic compound would be solid in its standard state as well. Okay, let's do another one. Okay, propanol. So this is specifically propan-1-ol, again forming, Jasmine, yes, all ionic compounds in their standard state will be solid. Yeah, okay. For propanol, again, we're forming 1 mole of the substance, so of the compound. I'll put the state symbol in there from the beginning so we don't forget, and they'll give it to you in the question, unless it's one that you're just meant to know. And then we want to form this from its elements. Again, feel free to race me and put your answers in the chat before I get there with the balancing as well. So made up of carbon, which is solid, or we could write the state symbol as, and often you'll see as solid, comma, graphite. And that's because we know that carbon exists as allotrope, so graphite or diamond or Buckminster fullerene, ... So graphite is defined as the standard state, but if you just wrote solid, not the end of the world, right? So carbon plus, wonderful, thank you, Harlem, plus H2 gas plus O2 gas, and then balancing, absolutely, 3 carbons, 3 hydrogens, and half an oxygen. Fantastic. Lovely, Zach. And again, make sure that you've got your state symbols in there as well. Without the state symbols, your answer is not correct. Okay, it wouldn't be giving the enthalpy change of formation. It would just be a nice balanced equation. Okay, are we good with this? Do we want to do one more, or do you think you're ready to move on? Oh, thank you. It is, well, hang on. 3, 5. I've got 3, 5, 7, 8. You're absolutely right. 4H2. Thank you very much. Thank you, Sienna. Thank you, Jay. Thank you, Grace. Okay, and Harlem, do you know what? I just trusted you. I didn't even check. Okay, but thank you. Well done for cross-checking for H2. Okay, let's do one more. Let's do the barium carbonate. Just to make sure that we are super, super confident with these. I'm just gonna do it down here. So we're forming 1 mole of barium carbonate, an ionic compound, which is solid, and they've told us in the question itself, and then forming it from its compounds. Barium is a metal, so it would just be Ba, solid. Carbon, we know, is solid, or we can say S, graphite if we wanted to. And then oxygen, we know, is O2. And gas, fantastic. So we would need 3/2 O2s, or you could write 1.5 O2 as well, absolutely away. And then that would give us 1 mole of our product. Okay, again, making sure your state symbols are in there, otherwise you haven't answered the question. Okay, I think we can move on. Let's go to standard enthalpy of combustion. Fantastic, thank you, Away. Making sure that you've got your definition. So again, in the chat, standard enthalpy change of combustion is, and always starts with, the enthalpy change when fantastic, thank you, Charlie. 1 mole of a substance, well done, Sam, is completely burned in oxygen under standard conditions. Actually, that's a good point. Do we put standard conditions in enthalpy of combustion? Because technically, if we're burning something, can we be at 298 Kelvin? Because we're going to have to heat it up to burn it. Let's put it in there for now. I'm going to put it in brackets and double check that. Or someone else, can you double check and come back to me? But what is important is all reactants and products. Yeah, to be fair, yes, standard conditions of pressure. I agree. Okay. All reactants and products in their standard state. Okay. Yes. Actually, this brings up a really good point, Jay, as well, for what we mean by standard conditions, because it can be a bit ambiguous. Technically, when it comes to enthalpy, all that matters, remember, enthalpy changes are heat energy changes at constant pressure. So really, when we say standard conditions, what we really mean, most importantly, is standard pressure. And then often you'll see the symbol look like this, so standard, and then they might write 298 to say standard at 298 Kelvin or standard 298, like that, to say that we're talking about standard conditions of temperature and pressure. But yes, absolutely, I'm going to get rid of these brackets because I agree with you. We're keeping our standard conditions. Okay. Now, oh, I saw a question earlier. I think I've lost it. Oh, Orla, completely reacted in oxygen. You can, or you can say in excess oxygen, and that would be the same as saying completely reacted. Okay. Now for our equations, complete combustion. Now, if we're just dealing with carbon, then carbon completely combusting in oxygen is going to give us carbon dioxide. And of course, we need our state symbols, otherwise we haven't completed our equation. So solid or solid graphite for the carbon, gas for the oxygen, and then gas for the carbon dioxide. Let's do the same with, let's do hexane, okay? So we've got C6H14 reacting in oxygen. We're going to balance this later. And when this combusts, so containing carbon and hydrogen, our products are going to be carbon dioxide and water. We want to, of course, make sure that our state symbols are in there. For the hexane, they've given you the state symbol in the question because you wouldn't necessarily know that otherwise, but for the others, we're expected to just know. Balancing, 6 in front of the carbon dioxide, 7 in front of the water, and then that gives us 12 plus 7, 19 oxygens. So 19 over 2 O2s. Okay, let me know if you agree or disagree. Feel free to shout at me in the chat if I've made a mistake. Does this look good? Wonderful. Thank you, Sienna. So let's relate this to Hess cycles now that we've actually recapped our definitions. Oops, where are we? There we go. So Hess's law, what this tells us is that if a change can take place by more than one route, then the overall change in enthalpy is the same, whichever route is taken. Okay, so whether we go directly from A to B, or we go from A to X to B, this enthalpy change here is going to be the same as this enthalpy change plus this enthalpy change. Okay, so whichever route we go by, if we're starting and ending in the same place, then our enthalpy change is going to be the same. Okay, now there are a couple of different ways that we can employ this. So let's start, right? And the reason that Hess cycles and Hess's law is so important is because some reactions we cannot measure the enthalpy change directly. Okay, it's great if we can just do an experiment and do some combustion calorimetry or some solution calorimetry, Q equals MC delta T, delta H equals minus Q over N times 1,000, get our number. But let's say we wanted to find the enthalpy change for the formation of carbon monoxide. That's going to be very, very difficult to do in practice, because if we start reacting carbon with oxygen, it's not necessarily going to stop at carbon monoxide. It's most likely going to give us carbon dioxide instead. So how do we make it stop at carbon monoxide and give us the precise and accurate enthalpy change for that reaction? The answer is we can't really. So we have to use Hess's law instead, going by an indirect route. Okay, we also might use Hess cycles or Hess's law if the reaction is like very fast, so like explosive, and so we don't want to do that in the lab, or if the reaction is very slow, and so again, it's not feasible to, well, feasible not in the chemical sense, but it's not realistic to do that in a lab setting. Okay, so two main types of Hess cycles and how we use Hess's law. One is when we've got enthalpy of formation data. Okay, so just as a general structure, if we were to write the overall equation that we're trying to find the enthalpy change for, so reactants, oh, wow, reactants producing products, and we're trying to find out what is the enthalpy change of reaction for this particular reaction. But we can't do that directly, but we've been given formation data. Now, because enthalpy of formation is forming 1 mole of a substance from its elements, what we can do as our indirect route is go via the elements. Okay, so then if we complete our cycle, absolutely, Nessa, the arrows go up, and that's linking with our definition. We know that enthalpy of formation is forming our substance from the elements, so the arrow has to go from the elements to the substance being formed. And again, from the elements to the substance being formed. Okay, absolutely, Miran, for combustion, arrows down. So this first arrow here is, we can represent that that's the enthalpy change of formation for the reactants. And then this second arrow, this is your enthalpy change of formation for the products. So now, how do we actually use this Hess cycle? Well, we know that as long as we are starting and finishing in the same place, it doesn't matter what route we take, the enthalpy change is the same. So if we're trying to find out our enthalpy of reaction, we are starting here and we're finishing here. So whether we go directly following this arrow from here to here, that's going to be exactly the same as if we start here, go down to the elements first, and then back up to the products, that's still starting and ending in the same place. Okay, but because we flipped the reactants arrow, this arrow no longer represents the enthalpy of formation for the reactants. It represents minus the enthalpy of formation for the reactants. Okay, so now if we want to calculate or write an expression for enthalpy change of reaction, so delta HR is equal to, following the arrows, minus the enthalpy of formation for the reactants plus the enthalpy of formation for the products. Okay, or to make this look a bit neater, because sometimes you might not want the minus to go at the front, we can just rewrite that as the enthalpy change for a reaction, if your given formation data is the enthalpy change of formation of the products minus the enthalpy change of formation of the reactants. Okay? And that's our general expression that we can use all the time. Well, not all the time. If we're given formation data, then this is the expression we can use. So if they don't actually ask you to draw a Hess cycle, you don't have to. Okay, and you'll often see sometimes these questions are worth, 1 or 2 marks. And so they're not expecting you to draw a whole Hess cycle. You can literally plug your values into this expression, and then you'll get whatever it is that you're trying to find. Okay, so let's do a really simple example before we get to the exam style questions. Let's say we had this reaction here. This is one of my favorites. You'll see it so much at A level if you haven't already. The contact process, you see it in the transition metal topic, in equilibria. They just love this equation. Okay, we need state symbols because otherwise none of our enthalpy changes actually mean anything. And we want to find the enthalpy change of reaction for this reaction. So let's say they asked us specifically to draw a Hess cycle using enthalpy of formation data or enthalpy change of formation data. So to complete the Hess cycle, when we're given formation data, we need to put the elements down here at the bottom. And it doesn't matter which side you look at for the elements because it's a balanced equation. So the elements and how many atoms of those elements will be the same on both sides, right? So is this balanced? Yes, it is. So down at the bottom for the elements, we're going to have sulfur, which is S. Now, of course, if you've already looked at period 3, you know that it's actually S8. So if you do put S8, that's absolutely fine. If you just put S, that's absolutely fine as well. Okay, I agree, just man, we can do S or we can do S8. Any mark scheme will accept either because they're not going to double penalize you for not knowing your period 3 chemistry in when what they're really testing here is the enthalpy change. Okay. You can't, it depends, Sienna. So if they ask you explicitly to draw a Hess cycle, you can't just write elements. You have to have all of the species down here and balanced. If you're just using the Hess cycle for your own benefit to help you figure it out, then you don't need to write a full, you can just write elements because that's more just for your own personal notes, right? Ooh, Zakir, I love that. Can everyone please read Zakir's message so that we can help to remember which way our arrows go? Formation flies to the sky, combustion claws to the ground. I love that, and I'm stealing it. So thank you so much. Okay. You might want to trademark that. Okay. So let's come back here. Lovely. Sulfur in its standard state is solid, but again, they would give you this information within the question. Oxygen, O2, gas, making sure that's balanced. We've got 3/2 O2s down here at the bottom. And then because it's formation flies to the sky. Formation flies, FF. So our arrows are going to go up. So this first arrow represents the enthalpy of formation for SO2. And we don't have an enthalpy of formation for O2, and that's because it's already an element in its standard state. So its formation enthalpy change of formation will just be 0, right? For our other arrow, this represents the enthalpy of formation for SO3. Yeah, Zakia, I think let's stick to your first one because the alliteration, I think, is what really gives it. Formation flies, combustion claws. Okay. So if we wanted to find our enthalpy change of reaction, that's going to be remember our expression, enthalpy change of formation for the products minus the enthalpy change of formation for the reactants. So that's going to be your enthalpy of formation for SO3 minus the enthalpy of formation for SO2. And then we will just plug those numbers in. Okay. Now, really importantly, and of course, when it comes to A level, it's very rarely as simple as that. Sometimes it is, sometimes they just kind of put in this extra one, but more often than not, you're given different values within the question, and then you're having to find something else, not the enthalpy change of reaction. But it's really important to have the system in place and then just read the question to figure out how you're applying the specific numbers in that question to the structure that you already have set up. Okay? How do you know in the reactant side oxygen is the one being added? So this is at the top, what I've written, that's just your overall equation for the chemical reaction that's taking place. So SO2 plus half O2 gives you SO3. And then the question is, use the formation data to calculate the enthalpy change of reaction. Okay, let's try an exam style question. That's a really good question, Harlem. The equation, it sometimes is the answer, okay? Sometimes the equation will be given to you, or they might link the equation to a definition that you should already know. So that's what we're going to do in this question here, right? So let's read this really carefully, because questions like this, again, tend to trip students up because we're talking about enthalpy change of combustion and enthalpy change of formation within the same question, so it can get really confusing. But the key is look out for which part is the equation and which part is the data that you're going to use to construct your Hess cycle. Okay, so here it says determine the enthalpy change of combustion of methane from the following standard enthalpy changes of formation. So because they've given us formation data, that means that we're drawing a formation Hess cycle. So formation flies, arrows going up from the elements. But because our overall reaction is combustion, that's what we're going to use as the equation that we're basing our Hess cycle on. Okay, so the equation that we're writing is going to be for enthalpy change of combustion for methane, which is CH4 plus O2 producing CO2 plus H2O. And this is what we're trying to find out. Okay, but because they've given us formation data, we're drawing a formation Hess cycle with the elements. So down at the, oh, this is not balanced. How embarrassing. 2 waters, 2 oxygens. What else is missing? I hope you're all shouting at your screen right now. State symbols. Absolutely. Okay, so down at the bottom, we need our elements so that we can draw a formation Hess cycle. So down at the bottom, we're going to have carbon plus 2 O2s plus 2 H2s, again with our state symbols. Our arrows are going up. This first arrow represents the enthalpy change of formation for CH4. This second arrow represents the enthalpy change of formation for CO2 plus 2 lots of the enthalpy change of formation for water. Okay, so now coming together to actually find, let me just change my pen color so we can see really clearly what's going on. To find this overall enthalpy change, remember that's going to be enthalpy change of reaction, in this case, which is combustion, is equal to your products minus the reactants. So that's going to be your enthalpy of formation for CO2 and 2 times your enthalpy of formation for H2O, all minus, and I'm going to use big brackets here, your enthalpy of formation for CH4. Okay, remember we're always going back to our core expression for products minus reactants if we're given formation data. Okay, Let's now plug those values into our calculators and be so careful with your signs here. That is, again, really, really common mistake that happens is just the transcription of the positive and the negative, how you're putting those numbers into your calculator. And I talk about this so much, and it's because I am personally traumatized, right, from this, because in my A level, like I said before, I ended up with 100% in my A level, but over the course of the year, I would drop so many marks on just nonsense negative signs in the wrong place because I was so overconfident that I knew what was going on that I didn't pay attention to the kind of small parts of the calculation. So make sure you are looking out for that, right? So we'll have minus 394 plus 2 times minus 286, and then that's all going to be minus 77, so plus 77. And I absolutely agree with Jay in the chat. That comes out as minus 255 kilojoules per mole. Okay, let me know in the chat if you agree with Jay. The reaction is absolutely exothermic, and that's a really good check, Moran, and I'm glad that you brought that up. I'm writing behind my face, and that's because when it comes to enthalpy changes, most have a designated whether they're exothermic or endothermic. So we can check if our answer makes sense by if it matches the enthalpy change that we're trying to calculate. So because we're trying to calculate an enthalpy of combustion, combustion values are always negative, always exothermic. So if you did this calculation and you ended up with a positive value, then you know you've done something wrong. Okay, absolutely, Jay. Okay. Actually, minus 25, so maybe do I agree with minus 255? Let me check my calculator. Let me know what you've got in the chat. Yeah, that shouldn't be 255 because remember, thank you, I'm putting it into my calculator too. The 286 is negative. So 2 times minus 286 and then plus minus 394. Let's put it all in its right place. So for this first side, what's going in this bracket, we should have minus 966 and then minus 77, so plus 77. Thank you, minus 889. Great. I agree, Charlie and Grace. I'm going to take back my agreements, Jay. I'm so sorry. Okay. Always double check your negative signs and make sure that it works with the numbers that you've got. We should get minus 889. The minus 286, Jasmine, came from up here. That's your enthalpy change of formation for the water. Okay. Should we do another one? Let's do one more before we go to the other type of Hess cycle. So here, slight variation where we are given the enthalpy change for the reaction, okay? And they want us to find the enthalpy change of formation for one of our species in that equation. Now, it's always important, again, to go back to the structure that we know and then put the values in that you have and then rearrange for what you don't have. Okay, so when it comes to when we're given formation data, we know straight away that our enthalpy change of reaction is going to be equal to the enthalpy change of formation for the products minus the enthalpy change of formation for the reactants. So it doesn't matter what they've given us in the question, we're still starting there. And then we can look at the values that they've given us and start plugging in the numbers that we've got so that we can rearrange what we don't have. So here, our products, that's carbon dioxide and water, right? So our overall enthalpy change minus 1,300 is going to be equal to the enthalpy, oh, hang on. Yeah, I'll write it with symbols first and then we'll put the numbers in afterwards, just so we can all keep track of what's going on. Okay, it's going to be equal to 2 times the enthalpy of formation for CO2 plus the enthalpy of formation for H2O, all of that minus the enthalpy of formation of the reactants, which is the enthalpy of formation for C2H2, which is what we're trying to find. Okay, again, remember, we don't include the oxygen because all elements in their standard state have an enthalpy change of formation of 0 because they're already in their standard state as an element. So now we can start to put the numbers in. Minus 1,300 is equal to 2 times minus 394 plus minus 286 minus our enthalpy of formation of C2H2, which is what we're trying to find. Okay, now before starting to rearrange and move things around, I want to solve these, I want to bring these numbers together first, just so I'm not moving around multiple expressions, right? So let's put that together. 2 times minus 394. Oh, is that the same as last time? I think it might be. Oh, no, it's not. 1074 minus 1074. Hopefully you agree. Okay. Let me know in the chat if you got the same thing. And then we are rearranging. So if you're not that confident at the moment with rearranging equations, please make that your number one priority before you go back in September, okay? Because that is so key, okay? That's the number one math skill that you need for A-level chemistry rearranging. So let's bring this, we can bring that over there, right? So add 1074 to both sides. And so we should get, I'm going to come up here just to give ourselves some more space. So minus 226 equals minus your enthalpy change of formation for C2H2. So then take the positive of both. 226 equals the enthalpy of formation for C2H2. Absolutely. Kilojoules per mole. Fantastic. Lovely, Moran, Becky, Jasmine, excellent. It's positive because enthalpies of formation can be either positive or they can be negative. Okay, it's all about the balance of the bonds making and breaking. So where enthalpy of combustion is always negative, enthalpy of formation can be either. Okay. Let's keep moving. Let's go to enthalpy of combustion, Hess cycles. Okay, any questions, please do put them in the chat. But again, the number one thing that I want you to take away from this is write out your expression, so your standard expression that you're going to use, and then stick to that expression, okay? Stick to that structure and then put the numbers in from the question in the appropriate places, okay? And then rearrange once you've got everything in its right place. Okay, because obviously it's going to be different problem solving each time, but if you've got your structure ready, then you're setting yourself up for success. Jasmine, yes, combustion is always negative enthalpy because it's always exothermic. Okay, Let's look at combustion. So we're going to go through this relatively quickly. So remember combustion, that's where we're burning 1 mole of our substance in excess oxygen. So when it comes to those Hess cycles, if we want to find our enthalpy change of reaction, so reactants to products, but we're given combustion data, enthalpy change of combustion data, then whereas with formation, we had the elements down here, when we're given combustion data, we have our combustion products down here. And 9 times out of 10, those combustion products are going to be carbon dioxide and or water, okay? But that's only if, of course, our species only contain carbon and hydrogen and oxygen. Okay, so typically, so carbon dioxide and water, those are typically the examples that you'll see. Hang on, let me answer these questions in order. So, Ambajit, the equation for formation and combustion, they're not the same. So we'll look at that right now. And Harlem, absolutely. If they mention a Hess law or a cycle, if they mention a Hess cycle specifically, or they might call it, instead of a Hess cycle, they often call it an enthalpy cycle. Okay, then you have to draw a Hess cycle. But if they don't, just go straight to the calculation. You can just use the expression. So as Zakir told us earlier, combustion, what was it? Claws to the ground. Okay. And that's because we know our definition is enthalpy change of combustion, 1 mole of a substance burning in complete oxygen, in excess oxygen rather. When it burns in excess oxygen, we're going to produce our combustion products. So now this arrow represents, this first one represents the enthalpy of combustion for the reactants. And then this one represents the enthalpy of combustion for the products. And this arrow, of course, that's your overall enthalpy change that you're trying to calculate. So now, as we saw before, and our Hess's law is that our enthalpy change is the same regardless of the route taken. So if we are starting here and ending here, that's the same as going down like this and then up like that. So this reactants arrow is exactly the same, but our products arrow has been flipped. So now it's minus the enthalpy change of combustion for the products. So if we were to write our expression for our enthalpy change, delta H is equal to the enthalpy change of combustion for the reactants minus the enthalpy change of combustion for the products. Okay, so formation, remember, was products minus reactants. Combustion is reactants minus products. Okay, and the way that one of my old students helped me to remember it, maybe she's here right now, I don't know if you are, let me know. For combustion, because it's reactants minus product, so CRP, so she would say cool record player. Okay, to remember that for combustion, it's reactants minus products. And then you just need to, oh, my head's in the way. And then you just need to remember that formation is the other way around. Um, Harlem, that works too. I'm not going to say it, but absolutely, that works too. Okay, feel free to read Harlem's message because I'm not going to read it. Oh no. Okay, so let's do a couple of examples. Going straight into kind of, actually, no, we're going to do the next one first, and then we're going to come back to this one because it's a bit trickier. Okay, so we have this equation. So make sure you've just skipped one question and go to the one for methane. So C plus 2H2 gives us CH4. We want to calculate the enthalpy change for this reaction. So we don't need to draw a Hess cycle. We can just go straight to our expression where we know that our enthalpy change for the reaction is our CRP. So our enthalpy change of combustion for reactants minus the enthalpy change of combustion for the products. Oh, it's first on your work. Amazing. If it's Great. I'm glad. Okay, so enthalpy change of combustion for the reactant minus enthalpy change of combustion for the product. So what we end up with for our reactant, we've got carbon. So that's enthalpy change of combustion for carbon, and 2 times your enthalpy change of combustion for the hydrogen, all minus the enthalpy change of combustion for the CH4. And then we can put our values in once we know what expression we're dealing with. If you want to skip straight to putting the values in, I'm not going to stop you. But again, just setting it out like this, it just avoids as many mistakes as possible, ultimately. And that is the goal. Okay. Oh, oxygen is involved. Let's come back to that in a second, Harlem. That's a good point. Okay, I did kind of gloss over it because we don't need it for the calculations, but I'll explain it in a second just to make sure it's as clear as possible. So putting those values in, we end up with minus 394. We've seen these numbers so many times now, plus 2 times minus 286. And then all of that minus 890. And we should get, someone tell me in the chat, I agree, lovely, minus 76. Okay. Feel free, again, if you're prone to making mistakes with negatives, to put everything in brackets, or combine everything in the brackets before you want to do the whole thing. Okay, absolutely, Jasmine. If you prefer the arrow way, fantastic. Choose whichever method works for you, okay, and will give you the greatest chance of getting it right every single time. Okay, the only reason that I particularly choose to use this calculation method is because the arrow way is nice if you know that you're looking for enthalpy of reaction, but when it comes to the rearranging, sometimes it's easier just to have it as a mathematical expression. But again, if the arrow way works for you, please keep using that. Okay? I'm going to come back briefly to this Hess cycle. Actually, I might have to draw another one. Actually, I'll draw it here, okay, to answer Harlem's question of where the oxygen's coming in, because you're absolutely right. They've given us combustion values, which means burning in excess oxygen. So if we were to draw the Hess cycle for this, actually, let me change my pen color so we're looking in the right place. So carbon plus 2 hydrogens gives us CH4. And then to complete our Hess cycle, down at the bottom, we need our combustion products, which are CO2 and H2O. Okay, balance those. 1 carbon dioxide, 2 waters. Now, we've got some oxygens that magically appeared, but that's fine. What we typically do is we put the oxygens over the arrow to show that they are involved in those enthalpy of combustion changes, but they cancel out, so they won't affect the enthalpy change for the overall reaction. So next to the arrow in brackets, we could write, we've got 1, 2, 3, 4 oxygens, so 2 O2s. So we can put plus 2 O2s on that bracket and plus 2 O2s over there to show that they're involved in the combustion that gets us down to the combustion product, but they cancel out for the overall equation. Jasmine, very, very, very unlikely. I haven't seen them give you an equation that's not balanced unless they explicitly ask in the question for you to balance the equation. Okay? They'll either say this is the equation, or they'll say write the equation, or they'll say balance this equation. But they won't just kind of sneak attack with an unbalanced equation and then hope that you spot it. That would be disrespectful, quite frankly. Okay. And Charlie, absolutely, you won't include oxygen in your calculations because the oxygen, oxygen doesn't have an enthalpy of combustion because if you burn oxygen in oxygen, you get oxygen, right? So it's oxygen's enthalpy of combustion is 0. And to be fair, same with carbon dioxide and water. Carbon dioxide and water don't have enthalpy of combustion values because they can't go any further. Carbon dioxide is as oxidized as that carbon's going to get. Absolutely, Henry. So yes, the reaction itself is not a combustion reaction, but because they've given us combustion data, we're using a combustion Hess cycle as our reaction pathway. Absolutely. Okay. Let's do one more to make sure that we have really, really got it. And then I do want to make sure that we have some time to go on to mean bond enthalpies. Hopefully we'll have a chance for at least one of those questions. And then in your pack, you've got some exam questions. We definitely will not get to do those today, but they're excellent practice for you to continue practicing with those. Okay. Let's go to our sucrose question. So we want to determine the enthalpy change of formation of sucrose given the following standard enthalpy changes of combustion. So this is similar to that formation question that we had where they kind of tried to confuse us by putting the words formation and combustion in the same question, but it's okay. They can't fool us, okay? Because they've given us combustion data, that means that we're using a combustion Hess cycle or the expression for combustion data. But because they've asked us to determine the enthalpy of formation, we're using that as the overall equation that we're basing our Hess cycle on. Okay, so the type of Hess cycle, I'm going to say it one more time. The type of Hess cycle or the expression that we use is based on the data that we're given. If we're given combustion data, we use reactants minus products. If we're given formation data, we use products minus reactants, regardless of what the kind of overall equation is that we're trying to calculate the change for. Okay, if that's not clear, please do let me know. So let's start by writing our equation, okay? Because that's the only way that we're going to get our like values correct. So enthalpy of formation, remember forming 1 mole of a substance, in this case sucrose, oops, C12, H22O11, from its elements C plus H2 plus O2. That's really messy. I don't like it. So I'm just going to draw that again. It's making me uncomfortable. C plus H2 plus O2. Okay, of course, and I hope you are don't scream, that's inappropriate. I hope that you are shouting at your computer screen or whatever you're looking at right now, state symbols, solid, gas, gas, and then for our final, they've told us in the question it's a solid. Making sure this is balanced. So thank you, Moran. So 12 carbons, 11 H2s, and 11/2 O2s. Okay, now if we want to draw a Hess cycle, we can, or we can go straight to our expression because we know that if we're given combustion data, our enthalpy change is going to be equal to the enthalpy change of combustion for the reactants minus the enthalpy change of combustion for the products. Okay, Sienna, luckily you don't actually have to know how to balance the combustion products, but if you wanted to, let's do that really quickly. Pretend the equation is up there. We're pointing down to, because we've just got carbons and hydrogens and oxygens, it would be CO2 plus H2O, okay? 12 carbons, so 12 carbon dioxides, 11 or 22 hydrogens, so 11 H2Os, and then we can put our balancing oxygens over the arrow. So 24 plus 11 oxygens. Hang on, is that correct? Yeah, 24 plus 11 oxygens gives us 35, but we've already got 11 taken care of, so there's only 24 extra ones. So that would be 12 plus 12 O2s over the brackets. Okay. Jasmine, you're way ahead of us, and I agree with you. Okay. Plugging those numbers in, just to make sure. For our reactants, that's going to be 12 lots of minus 394 plus 11 times minus 286. And then remember, oxygen doesn't have any enthalpy of combustion. That will just be 0. So we'll stop there. Minus, for our products, minus 5640. Have I missed out on oxygen? I don't think I've missed an oxygen, but let me know because there's 11 already in the reactants and products, so we're only adding 12 more. Okay, great. So when we put those values into our calculator, again, we might want to do one set of brackets at a time rather than put everything in, just in case. So you might want to put all of this together first before doing that bit. But again, that's only if you're a nervous calculator like me. Otherwise, if you're really confident with your calculator usage, then you can just put everything in directly. So we should end up with 7874 over there, minus minus, so plus 5640. And we get, just like Justman said before, I've lost your answer. Where is it? Oh no. Minus, where did it go? 7874. Sorry, that's minus. Minus 2234 kilojoules per mole. Okay, I agree. Okay, Jasmine, just double check because you're off by 6, which is probably just a transcription error. So something that you've just typed incorrectly in your calculator. Perfect, great. Okay, lovely. Okay, so once again, just like formation, we have our structure and then we plug our numbers into that structure. Let's, in the interest of time, let's look at some mean bond enthalpy calculations. Okay, unless you have any other questions for here. Okay, and you can save this last one for your own time. This one really, it takes about, 45 seconds. Okay. Let's go to mean bond enthalpy. Again, another definition. Absolutely, Harlem. So if they've given you combustion data, then you do the calculations for combustion. If they give you formation data, then you do the calculation for formation, regardless of what the overall equation is. Okay, look at the data that they give you, and that's the calculation type that you follow. Okay. Mean bond enthalpy. Let's see, are any of you typing away in the chat definition? The enthalpy change when I'll start off 1 mole. Ooh, I'm going to put it here. 1 mole of gaseous bonds are broken, averaged. Definitely revision for some definitions. averaged over a range of molecules or compounds. Oh, oh no. I need to revise my definitions. Averaged over a range of, oh, absolutely, sorry, it's standard conditions. Averaged over a range of molecules, compounds. Oh no, how embarrassing. Compounds. I knew it. That's what I was going to say. Okay. Definitions for mean bond enthalpy, where it's usually worth 2 marks. Okay. 1 mark for the 1 mole, and then the second mark for saying that it's averaged over a range of compounds. Okay. Moran, that wouldn't be necessarily mean bond enthalpy because the meaning of the mean is that it's averaged over a range of compounds. Okay. The bonds for the molecules need to be in the gaseous state, and we'll get onto that and how that comes into play in a bit, hopefully, if we've got time. Actually, we don't have time and we've got one more question, and I think if you're willing to stay, then we should just do it anyway. Okay, so when it comes to using mean bond enthalpies, what we need to consider is for a reaction to take place, we first need to, if we think of our energy profile diagrams or enthalpy profile diagrams, if we put that as enthalpy, and then we put that as, what is it, extent of the reaction. If we start with our reactants over here, what we first need to do, reactants, is we first need to break all of the bonds to give the individual atoms. Okay, I hope you're enjoying my square atoms. Okay, so we first need to break the bonds, and breaking bonds is an endothermic process. We need to put in energy to break bonds. And then once we've broken those bonds, then those atoms can, you know, join together in different arrangements, and that's going to release energy when we make the bonds to give whatever the product's going to be. Okay, and so breaking bonds, that's an endothermic process, whereas making bonds is an exothermic process. For this first diagram that I've drawn, we can see that the making of the bonds has released more energy than was required to break the bonds. So overall, this enthalpy change is negative, and so it's an exothermic reaction. Whereas sometimes, and I'll just do this as a really quick sketch, if more energy is required to break the bonds than is released in making the new ones, then we end up with a positive enthalpy change. And so overall, that's an endothermic reaction. Okay, but the key here is, and using these mean bond enthalpies, we need to break the bonds first, and then we can make new ones. Okay, so putting that together, we can now see that, and as our general expression, our enthalpy change for any given reaction is going to be equal to the sum of the bonds broken minus the bonds formed. Okay, so Jay, yes, you should be able to draw enthalpy or energy profile diagrams. You wouldn't put, these interesting symbols that I've put, but just having the reactants going up to the activation energy and then back down to product. You actually see it more commonly in the rates of reaction topic, so kinetics, rather than in the energetics topic. okay? Because this arrow here, that's technically the activation energy, okay? And you'll see it again in year 13 when you look at transition metals and catalysis in more detail, okay? So let's make sure we've got this expression down. This is what we're going to use, okay? Because remember again, we want to give ourselves a structure for all of our calculations. So regardless of what we're trying to find, we've got our starting point and then we just slot the correct numbers into the right places. Okay, but we've always got that starting point to structure our answers. Okay, so I reckon we've got time for a question at least. Okay, any questions? If you want me to go back, please let me know. So here, hydrazine can be used as fuel in rockets, has the formula N2H4, burns in the following reaction, for which the enthalpy change is minus 583 kilojoules per mole. Oh, I don't really like that. Kilojoules per mole, that's better, right? Determine the NN bond enthalpy in hydrazine. Use the following bond enthalpies. So it's very helpful to draw a sketch of all of the bonds so we know which bonds are being broken and which bonds are being made. So if we start with our reactants, where we're going to break the bonds, right? Because we always break the bonds in the reactants and then we make the bonds in the products. So let's start with the breaking. For breaking, we've got N2H4, and I've already told us it's a single NN bond, so we don't need to worry about that. And hydrogen can only make single bonds, so we know it has to look like this. And we're also breaking an oxygen molecule like that. And again, we know it's a double bond. They basically told us. And then for making, we're making an NN triple bond because that's what we've got in nitrogen. And for water, we're making the OH bonds. So now putting that into our expression, so delta H is equal to, actually, I'll do it twice, is equal to bonds broken minus bonds formed. So let's put all of our bonds broken. We are breaking an NN bond, single bond. We are breaking 4 NH bonds. And we're breaking an OO double bond. Okay, it's often worth just putting those numbers together and, getting the number, because often there's a mark for these sorts of questions for each stage. So don't try and chuck all of your numbers in at the end. Show the stages of your calculation because there are marks available for different stages. For your bonds formed, we're making an NN triple bond. And we are making, what else are we making? OH bonds, but we've got 2 waters, which means that we're making 4 OH bonds in total, because there are 2 OH bonds in each water molecule. Okay, now we've got our structure. Now we can put our numbers in. So our delta H, that's minus 583. That's equal to the NN bond, which is what we're trying to find out, plus 4 times 388 plus 498, all minus 944 and 4 lots of 463. Okay, let's start to put our terms together. So again, we're not going to chuck all of our numbers together straight away. I want to do a bracket at a time. So 4 times 388 plus 498. So NN plus 2050 minus 2796. Okay, actually I can get rid of that outside bracket. Now I can start to put those numbers together. So 2050 minus 2796 minus, I'm going to give myself some space, where up here. So minus 583 equals NN minus 746. Bring the 746 over to the other side, right? And we should end up with 163 kilojoules per mole. Any questions? The chat is pin drop silence. I'm guessing because your hands are all busy with your calculators. Amazing, Andreas. Well done. Okay. We got one happy student. Who else is okay with this? Lovely. Well done, Charlie. Fantastic, Sienna. Lovely, Miran. Okay, so remember, and I know I keep repeating myself, but I'm actually not sorry. I will keep repeating this because, again, I have marked hundreds of like student tests, okay, in my time. And these bond enthalpy questions, for whatever reason, so many students do so terribly in them, but they're not really that difficult. But there's a lot going on, okay? And I understand why there are mistakes made, but the way that you can limit those mistakes is by structuring your answer. So going back to the foundation of what expression am I using, and then now look at the question and start to put the different pieces in and rearrange to get your final answer, rather than kind of panicking and going, oh my God, there's too many numbers. What do I do? Okay, if we start with the enthalpy change is equal to the bonds broken minus the bonds formed, you lay out with no numbers which bond you're breaking and which bond you're forming. And only once you've got that laid out and you've double checked that your balancing for all of that is correct, only then do you put your numbers in. Okay, your numbers should be the last thing that you put in because the numbers only go in once the expression is exactly kind of as you need it. Okay, and you figured out where all the expressions are going. Okay, do we have any questions here? Lovely. Thank you, Grace. Okay. So we are out of time, but however, I want just to talk to you so quickly. I hope you can stay with me. Did I ask you last? I think I asked you last week if you could stay with me for an extra 10, 15 minutes. I'm going to use a little bit of that extra 10, 15 minutes just to give you a hint about this question, because I do want you to have a go at finishing it off in your own time. So this question is almost identical to the last one that we did. So you can work through it in exactly the same way using the method that we've got previously. But there's one extra piece of information, and that is here. Okay, that is the enthalpy of vaporization for ethanol. And that's because in the equation for that we're trying to find the enthalpy change for, the ethanol is a liquid, but for using mean bond enthalpies, everything needs to be a gas, which means that there is an extra enthalpy change. Okay, so as well as including all of your bond enthalpies, you also have to add the 44 that turns the liquid into a gas. Okay, so look out for questions like this where you've got an extra change to consider. Okay, any questions there before I start talking to you? about how you can stay with me for all of year 13 and we can get really, really ready for your exams. Okay, great. Okay. Before we go through and like I talked to you about the main course, could you please, if you liked this session, please press like. Okay, it really, really helps out. And if you're not yet subscribed to the channel, make sure that you do subscribe. At the moment, it's only, our live streams that are up on the channel, but very, very soon there will be kind of actual lesson YouTube videos coming up as well. So that is in the works. So make sure that you are subscribed. Okay, fantastic. Thank you so much, Harlem. So, oh, I'll leave these questions for you to practice. So you've got plenty of practice here. But what's really important, even just about those practice questions, is that if you sign up for the full course, of course, you've got your taster now for the summer school, but the full course runs from September until May. Thank you so much, Desmond. And so from the second week of September all the way up until May. So a total of 108 hours of lessons, where you'll get the exam style homeworks and video solutions for every single lesson. Where for the summer school, so far you've been getting 3 questions, right? And they've been multiple choice. For the full course, you get 5 questions. Mostly written questions. There will be some multiple choice dotted in there as well. And you'll also get monthly assessments to make sure that you're bringing all of your knowledge together from the whole course. Okay, on top of that, especially if you're in the pro course, which to be fair, most students that sign up to our courses go for the pro course, and that's because the mentor support is so incredible. So mentors are typically university students at the top universities in the country that got, A stars in their particular subject. So they'll have A stars in chemistry, eights and nines at GCSE. And so um, you'll have complete access to them. I mean, within reason. Of course, they might not be able to answer immediately if you message them in the middle of the night, but it means that if you've got any questions about the lesson that you've just done, if you've got any lessons about the homework, if it's a lesson like this where we've got, some exam questions at the end for you to have a go at, and you want some support with those exam questions, then your mentor will be there to help you through those questions. And you can ask all of these questions that you're asking me in the chat, but as you're doing your own work, not just work from my headspace, if you've got work from, your schoolwork and you want a quick question to ask them, then you can ask your mentor as well. Okay. And hopefully you're already used to having live lessons, okay, on a great platform. I hope you're enjoying the platform. The lessons being recorded, you've got your workbooks and your materials, and you've got each other to support as well. At the moment, you've just got each other in the chat, but as part of the main course, you're all added to a Discord channel, and so you'll be able to talk to each other and help each other out outside of sessions as well. Okay, Zara, great question. And I'll get on to, actually, no, I'll answer you now because it's in a few slides' time. For chemistry in particular, and this is really great, there are 2 chemistry teachers. So there's myself, I'm the head of chemistry, and then we also have another chemistry teacher, Devinder. So Dav does chemistry, if any of you have seen his stuff before. So it means that we're able to cover 2 exam boards. So I will do all of the sessions for AQA, and then Devinder will do all of the sessions for OCRA. Okay, so both exam boards there will be covered. We chose those 2 exam boards because those are, the most popular ones that we've seen across the country. But also, if you are an edXL student, edXL and OCRA are really, really similar. So you could still get a lot out of the OCRA course as well. Okay, so worth considering. And if you have any extra questions about that, if you're not doing AQA or OCRA, please type in the chat and let me know. Okay. Looking at the prices, and to be fair, this will be some information that will be really useful for you to share with your parents, okay, if they're around right now, or if you can share it with them later. So typically, as you may already know, private tutors are very expensive. Okay. And I say that for myself as well. I used to be a private tutor up until I started working with my headspace, and I charged a lot, okay, for an hourly session. So depending on the experience, going up to, 100 to 200 pounds an hour. You may have even seen on Physics and Maths Tutor when you see those ads, how much private tutors are charging. And these are just a few that we found of the kind of different levels of private tuition. So over the course of the year, if you had two lessons a week, so 80 lessons a year, then that would come up to almost £5,000, right? And also add some extra challenges of, trying to find a tutor, trying to schedule the right time for those lessons and work out the timetables, not necessarily knowing if the tutor's going to be any good, no offense to them, not having access to the sessions afterwards or extra study materials, and not necessarily having like a planned session. Sometimes for one-to-one tuition, it's kind of, in the moment ad hoc. But then, of course, my headspace, woo, woo, woo. Okay, so comparing the value, let's say instead of £4,800 for two lessons a week for your subject, then instead it's over the course of the year, £1,080, again, depending on your course. That would be the maximum for a whole year with my headspace. So about 5 times cheaper. Okay. But on top of that, and this is why if you're still here, I'm glad that you are, anyone that is in the summer school, so you get a massive discount because you've engaged with My Headspace already and you're already, on your journey with the course. So you can get more than 40% off by using a special code. If you go to I think the link is in the description. I really hope so. If it's not, let me know. But instead of between 800 and £1,100, instead you're going between, 397 to £597. Again, that's for the entire year of courses. So from September up until May. Oh, that's a really good question, Charlie. That is a very good question. Let me find out. Actually, do you know what I'd like you to do? If you still message that code, and then they'll be able to talk you through whether or not it's still applicable. Okay? So still use the code and then find out from there. Okay, so summer 2024, going to the link in the description, and then you get that massive discount for the entire year of the course. That balances out. I know it looks, I mean, I won't say it doesn't look like a lot. £600 still feels like a lot of money. But breaking that down per lesson, oh, we'll go on to that in a second. Let me just find it. But there's a 14-day full refund guarantee if you don't like it, so no risk. And if you break that down for each lesson, it works out at oh gosh, I wish I could do the maths. Really cheap, less than £5 per lesson. I think with that discount, less than, £4 per lesson, really, per hour. And it's not, you can pay in different ways, so you don't have to pay all of it up front. There are different installment plans so that you can pay over the course of the year. Okay, so it's not a one-time payment unless you want it to be. Okay. What does DOW mean? Oh, I want to know. Okay. Now I've spoken to you about absolutely, and don't forget, speak to your like parents and carers as well, so that you're not having to worry about just this off of your own back. And lots of you doing chemistry, I know that very common subject combinations would be to have maths, to have biology, to have physics as well. And so we've got, of course, subject experts across those subjects. Are any of you in any of the other summer school courses? So I'm guessing a lot of you will know Neil already and Laura, because they've been here for, a good chunk of time. Okay, and their social media pages are crazy, absolutely. So for maths, for biology, for physics with Brooke, for chemistry, and as I mentioned before, we've got two chemistry teachers. So we've got me, and I'll be running the AQA course, and then Dav, who'll be running the OCR course. Absolutely, Ishak, though, just like with the summer school, if you miss a session, all the sessions are recorded, so you've got access to them all. Okay. There's also a uni prep course, which is run by the head of English. So that's, tips for UCAS, personal statements, interviews, all of that stuff to make sure that you feel as ready as possible. Okay. And so there is a special pass at the moment, which is brand new this year, which is called the Ultimate Pass. And that's because we recognize that most of you, sorry, it's so weird looking at my face just right there in the middle. Most of you will be doing multiple subjects. Okay. So for access to all of your subjects, let's say you do biology, chemistry, and maths, then you can get all three subjects together as a package, but for much, much cheaper than if you were to do each subject individually. Okay, so for the ultimate pass, which is all three subjects, that is maximum just under £1,500, which averages out to about £2 to £4 an hour. So for £4 an hour versus £2 an hour. Okay. And again, that's for three subjects. So if we think one subject was, £600, all three subjects for 1,500. So already we can see how much of a discount that is on top of your existing discount. As Sienna's question earlier, which is a great question, the price can be split into installments, so you're not having to worry about paying it all at the same time. And the price of the installment will vary depending on whether you go for the standard package, which is on the cheaper end. So that's without the mentor support, or the pro package, which is where you get that 24-hour mentor support. Okay. Remember, so if you are interested in this, and again, please do speak to your parents and carers and whoever would be either paying completely or supporting you with paying for this course. Talk them through this as well. They can go to the website, they can send the WhatsApp message so that they can have the conversation with our customer service team and our sales team so that they get all of the information and aren't just, necessarily trusting your word for the package. They can make sure that they talk to the team as well. Okay. Do we have any questions before I leave you for today? Any questions? Are any of you still here? Am I talking to myself? Maybe. Oh no, there's a few of you. Okay, great. Oh, okay, you're very welcome, Amaji. How did I get 100%? Okay, I meant questions about the course, but if you're still here, then you're committed. So I'll tell you how I got 100%. So there's a few different ways that all came together. Number one, and I think this, I can't downplay this, right? Um, I just got the chemistry, right? It's one of those, it kind of clicked for me. Okay, so I didn't necessarily buy Sienna and buy everyone, and let's stick around if you want to hear how I got 100%. But if you have had enough of my voice for today, which is fair enough, then I'll see you on Friday. Okay. So the chemistry did click, so I won't lie to you there and say that I started at a U and then struggled my way up. I did get it, but the number one thing was pre-reading. Okay. So one of the things is, so I studied chemistry at Oxford, and so my Oxford interview was in December, right? Was it in December? Yeah, around December. So before going to my interview, I basically taught myself the rest of the A-level course before my interview because I wanted to be as prepared as possible. I wanted to be that no matter what topic they asked me about, even if I didn't understand it fully, I had at least a kind of broad enough concept that I could have like a way into that question. Okay. On top of that, and in the run up to my exams, I did, and this is the number one thing that I would recommend for all of you as well. So, as well as pre-reading, not necessarily the whole course in advance, because that was kind of ridiculous. I wouldn't recommend that. But pre-reading and pre-learning, like the next lesson or the next topic, not so that you 100% understand it, but so that you're not going into it completely kind of like shell-shocked with everything being new information. And then do every single past paper question that exists. Okay. When I went into my A-level exams, there wasn't an A-level question that I hadn't seen. It didn't matter whether it was from my exam board or from a different exam board. So I did AQA. Did I? Yeah, I did AQA, but all the other exam boards, I did their questions as well because the chemistry is the chemistry, and I didn't want to be surprised, right? You want to see all of the different ways, or as many ways as possible, as they could ask you a particular question or ask you to apply a certain kind of area of your knowledge. Okay. And the final part is attention to detail. And I mentioned that before with like my negative signs. Once you spot that you're making mistakes in particular places, make sure that you spend a really good amount of time addressing those mistakes and then practicing again to make sure that you're not making the same mistake again. Okay, often what happens is we do practice questions, we mark them, we go, okay, yeah, these were wrong, these were right, and then we never look at those practice questions again. And it's like, how will you get the ones that you got wrong right the next time unless you're actually then putting in the work for those particular areas that you spotted? So it's that kind of reflective cycle as well. Okay. But when you join me in the main course, which I hope that you do, we'll go through so much exam technique and like a deep understanding of the content so that you're not just trying to kind of hold everything in the front of your mind and regurgitate it, because that's often where things go wrong, but you really fully understand it and have the systems and structures to be able to work through even the trickiest of problems. Does that answer your question? Sorry, that was a really long answer, Sam. Okay, any other questions? Please let me know. Otherwise, I will wish you a wonderful, you're very welcome, a wonderful week. I will see you on Friday for our next lesson. Make sure you do the homework. Watch the video solutions as well to make sure if you get any of them wrong, that you understand how to get them right the next time. Okay, you're very welcome, Hal. Okay, lovely. Bye. Thank you, Ishak. Okay, Fuzzy. Bye. Bye, Charlie. Bye, bye, bye.